Okay, these are the solutions to homework number 10. I've started out with giving you the formulas for midpoint and trapezoidal rule. And the first problem was to write down the proof for the midpoint rule. But using the trick we used in the lecture for the left endpoint. So it really parallels what we've done in the lecture, I think it was 6.1. And the ingredients to this is that we're trying to approximate the function, the integral of f of x, and we're doing this by replacing it by the integral of p of x, where p is the interpolating polynomial. And we know the error of the interpolating polynomial. And we want to use linear interpolation. So we could use, since it's the midpoint rule, we could run through this and do constant interpolation, but then we would get an error bound, which is order h. And that is not as good as we'd like it to be. So we can do better using this trick. So with linear interpolation, the error bound for linear interpolation is this formula here. So this is something we dealt with extensively in chapter 4. So now what we're doing here now is that we're saying that rather than looking, so this is midpoint rule. We're tilting this line here so that it eventually lines up with the function value at the point xk. And the error of this rectangle is the same as the error of the trapezoid. The area, not the area, the area of the rectangle equals the area of the trapezoid. And that is just because of the area formula for the trapezoid. Okay, so now this is our setup. So we created this artificial node. And so now this gives us this L of x here, which is x minus the midpoint times x minus the left endpoint. Now, what's happening here that our interpolation points are these two here, but we're also checking out the error over on the outside. So we sort of, you want to be extrapolating, but our interpolation error formula does take this into account. So this is perfectly okay. Okay, now so we have to integrate the L of x, right? Because, we're having this term here. So we integrate the L of x and move from the integration interval xk plus 1 to minus h over 2 h over 2. We obtain this formula here. So the L of x from xk to xk plus 1 is the same as from minus h over 2 to h over 2 t times t plus h over 2. So this is for the left endpoint, and this is for the middle point. So multiplying this out gives us the integral from minus h over 2 to h over 2, t squared plus th over 2 dt. And this integral is 0 because of symmetry. And so we're only left with the first contribution. And so that gives us an h cubed over 12. And that is only half as big as we would get for the trapezoidal rule. So again, we're summing up over all the subintervals. So nh equals b minus a. And then we're using the k2 as the error bound. And so that in the end gives us the error formula for the midpoint rule. Okay. Next thing here is a little example of basically just using the formula that t of h over 2 is 1/2 t of h plus m of h. So we can get the trapezoidal rule for half the step size by averaging the trapezoidal rule and the midpoint rule for the step size h. And so therefore, this is just the average here. So that gives me this number 43 over 64. And then it's a question of doing some arithmetic. The exact value of the integral is 2/3. So why is that? Because it's the integral from 0 to x squared minus x dx. That would be 1 over third x cubed minus x squared over 2 from 0 to 2, right? And so this gives me, the first term here is an 8 over 3 minus an x squared is 4. So it's 2 here, 4 over 2, 2. So this is 2/3. So this is where this 2/3 comes from. And then you just have to take the differences, and this is just using rational numbers. So you can see the error of the trapezoidal rule is twice as big as the error for the midpoint rule. So twice as big as this one here. And then when we go to t to the 1 over 8th, we're seeing that the error gets divided by 4. Okay? And so this is all as predicted by the theory. Okay, moving on to the next problem here. Find an error bound for the left endpoint approximation, left rectangular way. And in some ways, this is similar to question 1, but it's actually easier because the interpolation error formula is simply the mean value theorem, right? So this is what the error of interpolation in 1 point says. It's a constant only, right? So this is the f of xk equals that interpolating polynomials. So it's a constant. And then we're assuming that we have a bound for f prime. And if we integrate this now, we get for each subinterval, we're integrating x minus xk. So that will give us an h squared over 2 for each subinterval. Okay, so the k1 comes from the f prime, and this comes from taking the integral of x minus xk dx from xk to xk plus h. Okay, and this is really just looking at the area under the triangle here, right? So that's that, and that if you sum this all up, we get this error formula here. So you can see that it's only order h, which is to be expected, and the first derivative bound goes in here, and of course the length of the interval. Okay, number 4. So this is quite similar to some of the iClicker questions I asked. So that using MATLAB, want to find out what is the exact integral. And since we're integrating over an integer multiple of the period, the exact integral is 0. But when we actually do the computation with this function here, we get the wrong answer 2 pi at first. And after n equals 16, we get the right answer. And so this has to do with periodic functions. When you look at the function values here with n equals 8 subintervals, you can see that I just happen to evaluate the function at all places where it's equal to 1. And since I'm integrating over the interval from 0 to 2 pi, the trapezoidal rule gives me 2 pi. If you go with the problem number B, where we go from the interval is 0 to 2, then we no longer have periodicity, and the errors behave just the way we expect them. So nothing too exciting. So here's the interval with 0 to 2 pi, and you can see that up to here we're getting 2 pi as the answer, and then we're basically getting 0 as the answer. If we do problem number B, you can see that the errors behave like order h square, meaning every time I half h by 2, I get an error which is only which is 4 times as small. Okay, perfect. And the last thing was the problem from the text, where we had to code the Romberg algorithm, and there were a number of examples there. So if you go back and look at that, you can see what this is referring to. I think the first problem had something like a cosine of square root of x in here. And so that is, if you call a singularity, in the sense that if you take the derivative, it blows up, okay? Because we got the square root term in here. And so Romberg doesn't help because the expansion isn't valid, because the expansion relies on all the derivatives uh, being exact. Now, for monomials, I think it was x to the 7 or something like that. At some point, one of the Romberg columns will show the correct answer in its top entry and will give it the exact answer, simply because the order of the method is so high. When you have a periodic function, you don't see a speed up of the job because the trapezoidal rule is already as good as it gets. So, and this has to do with the fact that if you have a periodic functions, the coefficients in that expansion, which we eliminate, are all equal to 0. So eliminating them doesn't help. And lastly, for that last example, the derivatives are small at the endpoint, so the coefficients for the expansion are small. So the improvement of using Romberg is only somewhat limited. And that would be the solution to homework 10. This is the solution to our last quiz, quiz number 10. Okay, the first thing was really an example we did in class, except we didn't do Simpson's rule at the time. And you can do this, of course, the exact answer here is 2/3. And we know from, trapezoidal rule will be equal to 2 because we will just evaluate these points. The midpoint rule is 0. And Simpson's rule, you can either calculate it directly as 2/3, or you know that it's going to be exact for polynomials of degree less than 3. And so that leaves us with 4/3, 2/3, and 0 as the errors, and that is the exact answer. Going on to the next one, this was really just using the fact that t of h over 2 equals 1/2 of t of h plus m of h. And so since we know what t of 1/4 and m of 1/4 is, we know that this has to be the average of these two values here. And admittedly, that requires a bit of fractional work, but the answer is 19/8. This was the first time I sort of asked you sort of a question like that. Clearly the error here gets roughly multiplied. This seems to be more like order h, and it's not order h squared, right? Because every time I divide h by 2, the error only gets divided by 2. So it's order h. So why is it like that? So it could be any of lots of reasons, but the problem is with my code here, because the trapezoidal rule has 1/2, would it be at f of a plus all these other things, and at the end it has to be 1/2 of f of b. And then when you look more carefully, really what happens here, because in our case, this doesn't matter, because if we have x to the 7, then f of 0 equals 0. So even though this is an error in the code, it doesn't change the result. But here, the f of b with x to the 7, that equals 1. So instead of 1/2, we're having 1, but it gets multiplied by h. So that mean we are making an error of order is h over 2. And so that's the error we're seeing, and it comes from the code not doing this correct. Okay, a little bit of a thing. I suppose some of you thought that I wouldn't dare to publish a code which is incorrect, but so it is. Now, this problem was actually in some ways the most sophisticated of these questions. And it's, however, fairly easy to see, because from this relationship, we can deduce that m of h equals 2 times t of h over 2 minus t of h. So it's almost the inefficient way of computing the midpoint rule by computing the trapezoidal rule with h over 2 and then subtracting some of the values you got with t of h. So this just comes out of the algebra here. But this can be expanded in a series in h squared, and this is a series in h squared. So m of h will indeed look like j plus some constant d1 h squared plus d2 h fourth. So the answer is true. And that was the last question, except there was the thing that our midterm happens to be on August 13 at 3:30 p.m. And this was just served to be as a reminder that you're ready for this and that you will be present and show up a little bit early so we can do all the things we need to do. And this was the solution to your very last quiz, possibly your last Macm316 quiz ever. So quite a historic moment. Okay,